talk about the conjugate theorem, okay? So the conjugate theorem, it's saying that if a polynomial with rational coefficients, then the irrational roots P of X equals 0, okay? Occur in conjugate pairs. That means that you cannot have a complex number without its friend when you're finding the roots. So when you have A plus B plus the square root of B, there's also another root that's going to be A minus the square root of B. Yes. Okay, now with that same thing in mind, if you have A plus BI is a 0 of a function, then therefore, using that same logic, A minus BI is also a 0 of the function. Okay, if you have a polynomial function of odd degree, there has to be at least one row 0. Okay. X equals 2, X equals 5, X equals 2.5. Because you're actually crossing the x-axis. All right, so good point was brought up. Let me make it very clear. Something is called a real 0 if I cross the x-axis. Does that make sense? So I'm crossing the x-axis. This is a real 0, right? Does that make sense? If I'm right here, will this function ever cross the x-axis? So it has imaginary zeros. Yes? This function here, will it ever cross the x-axis?
It has to have you have to like make up an imaginary one. Not.
No, you'll be able to calculate it.
Yeah, what's the point of having them if they're not actually like...
So what they have, where it came from is that when people started graphing and trying to make predictions of what was happening, the functions they were creating weren't crossing the x-axis.
Wait, so like predictions of what? Like weather?
So if they're analyzing the trajectory of something and they were trying to say, okay, over time, I think it'll project blah, blah, blah. And they take their data and they run their numbers. They're like, okay, here's our function. And when they graph the function, they realize, oh crap, part of this function doesn't touch the x-axis. What do we call those numbers? And they're like, oh, they're imaginary because at this point in our function or at this point in time, it does not cross the x-axis.
One person that did this?
I'm pretty sure it's a collective group of people.
Why do they do that?
They call difficult numbers or something?
What? I'm sorry.
Numbers.
Like, why do they have to cross it?
That's what we learned about yesterday.
Like, why do they need to have a 0? Like, since they're imaginary, why do they need to like? Yeah, like what did they?
I don't know how to answer that question.
They saw the equation, like, oh, there's not a 0. Why did they find the need to make find?
I think they just found a need to define it and say what it is and why it's happening. So this happens because of this, and this is whatever the problem is or wherever the foundation is. I'm sorry, guys. I wish I was a math encyclopedia for you and that I could sit here and tell you the reason and rhyme to every single thing in math, but I'm not Google. And so therefore, I can tell you as much as I know, but if you get really bored and antsy, you can Google it. Okay. Too bad he's not here to do it for y'all. But so you guys can definitely look it up, but I'm giving you just based on what it is. That's why the imaginaries came into play, is that once these functions came out, they're like, oh no, my graph looks like this. I didn't cross the x-axis. Okay. That's just a general reason for that. Okay. I think that you're focusing too much on the why and not enough on the how. And that's going to be the biggest problem because this is not the history of mathematics. This is not a theories class. So yes, in college when I had to. But yeah, we're on the how. How do you do it? How do you find it? How do you apply it? Okay. All right. So a polynomial function of f degree 5, whose coefficients are real numbers, has the zeros x equals 2, 3i, and 1 plus I. Find the remaining zeros of the function. Okay. So using the fact up here that we wrote for a conjugate root theorem, if I know one of my imaginaries, then I automatically know there is another imaginary. Okay, they come in pairs. Imaginary roots come in pairs. You have a positive and a negative for every imaginary root. Okay, so here we have our first root. Our first root is x equals 2. So I can write that in factored form. If I have x equals 2, then the factored form is going to be x minus 2.
Wait,
So this is our factored form. So they gave us our zeros, our roots. If I have 3i, that means I know x minus 3i. Because it's imaginary, it has to have a friend that goes along with it. That friend would be x plus 3i. Oh, fudge.
Oh my goodness.
There we go.
Oh, yeah, good job, miss.
This
Okay.
is like a really small.
Huh?
Oh, yeah.
Right?
What'd you say?
Like 3 eyes, I'm supposed to have 2 of them, right? Like, the positive, negative.
Yes.
Oh, wait, so wherever there's an I, an imaginary number, we always have to have.
They always have a pair. That's what that's what this theorem is telling right here. If I know this one, then I automatically know that one, the other. They go together.
Like plus minus.
Yes. Oh, thank you. Huh? It's I can't hear you. Yes. So here we're at x. Now, this is where it gets tricky when you have the 1 plus I. Whatever your real is, that's gonna be the sign of both of them. The only sign that's changing is this one. So I have x plus 1 plus I, and I'm gonna have x plus 1 minus I.
Oh, wow. X plus 1, plus 1 plus I. Minus.
Because they're all gonna have their opposite. So your i's, that's it for your zeros. Those are your zeros in factored form. It's all together in one. So these are your zeros. We have 2. We have negative 3i, positive 3i. We have 1 plus I and 1 minus I. Those are my zeros, my real and 4 imaginaries. Yes.
Oh, why doesn't it? Yeah, why on like the second, or like why on the very last one? Why isn't X minus 1 minus 1?
No, only for conjugate, not conjugates, complex numbers as factors, only the second operation change. Does that make sense? Only the second operation change. If it had been, I just want to make sure that we understand. So I'm going to do this one. So if I had negative 1 plus 1, right? Plus I, plus 1 I, its factor would be x, oh my gosh, pen, minus 1 plus I, and the other one will be x minus 1 minus I.
Okay. What is that an I?
Okay, does that make sense?
Yeah, I was gonna ask that
That
too.
looks
Why
like a
don't we
face.
change the eggs?
Only the second operation changes.
Oh,
Okay.
okay. Yeah, I felt like that was a stupid question.
No, it wasn't. It's a very valid question. That's why I said, let me clarify that for you. So if the first term depends on your real part of your complex number. So if your real is negative, then your first operation is going to be minus negative, right? If your real is positive, then your first operation is going to be plus.
Wait, did that like come into play later?
It's between these two. So
But does it matter? Like,
mathematically, when you distribute, yeah, yes. Okay, so now that you have these factors, on the next part, we're going to, I think, write the factors and multiply, okay? It's gonna take you back to the original polynomial, okay? So this is a factored form of the polynomial. Through distribution, we're gonna find the standard form of the polynomial, okay? So let's make sure we're okay again, setting it up. So for this one, it says, so I can see, find a polynomial function f of degree 4 whose coefficients are real numbers and that has the zeros 2, 2, negative 3 plus 1. Assume a equals 1 for the leading coefficient. So we want to end up getting it in standard form, okay? If we don't have it in standard form, we're not able to graph it on the calculator. And that's because it has imaginaries, okay? So hopefully I left you enough room. I'm going to say I did.
You did.
yeah.
So the first thing we're gonna do is write this in factored form.
So it'd be like X minus 2,
There we go.
plus 2.
They're both positive 2s. So
Minus 2.
you have x minus 2 what? Squared. you'll have x minus 2 squared, right? If I have 2 zeros at 2, it's telling me that it's a double root at 2. It would be like a kiss at 2.
Oh,
Negative 3 minus I.
So it'd be x minus 3 minus I times x minus 3 plus I. Is it different than what we just did? Yes.
so
No.
if you wrote this out, it was x minus 2 times x minus 2.
Right,
that's
I'm
x
doing
plus
Wait, so wait, could we write it?
Because it was positive.
Right, so what I'm
You
saying,
don't
you know when we did x minus 3i and then x plus 3i all for one?
Yes, that was just for this 3i. So 3i has a negative and a,
Only to the opposite.
we did its opposite too. I just wrote it this one first.
No, I'm saying that.
Just the two.
Just the two and don't do the plus.
It doesn't have a pair. It's just what it is. Your reals don't have pair. Just your imaginaries have the pair. It's just a regular factor. Yes. Okay, only your real, so a question came up, shh, guys. It came up, explain when do you have the pairs? Only your imaginaries have automatic pairs, okay? Only your imaginaries have automatic pairs, not your real number. If there's only one x equals 2 given, then you only have a factor of x minus 2. Does that make sense?
Yeah.
If I'm only given x equals negative 2, then the factor is only x plus 2. Remember we talked about our x's are what? Liars. So even though it looks like it's going to be positive, when we write it, it's written as a negative. Okay. All right. So this is it in factored form. Are we okay writing it in factored form? That's step 1, is getting it in factored form. So taking our zeros and write them in factored form. We're good?
Wait, that's like. That's where the two is, like she's showing us.
Wait, would it be like a little curve like that or?
It could be up or down. I didn't draw the whole, I didn't draw the whole thing out, y'all. But it's always good. If it's a square, you're either kissing from the top or kissing from the bottom of the x-axis. I don't know.
Good. Much easier.
All right, so once we're writing it, are we good? Okay. So now you have your factored form of your problem, and you just keep going. Are we ready to keep going?
Yes.
So now you're going to distribute. Lots and lots of multiplication. My pen hates me. Yes. So x minus 2 squared, that's a pretty easy distribution. That's going to become x squared minus 4x plus 4. That one's done. When you have a square of something, you are adding it, you're doubling it and squaring it, right?
Yeah.
So negative 2 doubled is
4.
negative 4, right?
Yeah.
Negative 2 squared is 4. That's it. That's done.
Yep.
So just to make sure we understand that concept, if I had x minus 3 squared, when you're squaring a binomial, all you're doing is doubling and squaring. What is negative 3 doubled?
Wait, it would be x.
Negative 6, right? What is negative 3 squared? Negative 3 squared is 9. So x minus 3 is x squared minus 6x plus 9.
Oh, we get stuff in the parentheses. We do. No, we go to.
Where do you see? It's just foil. It's just shorthand foil at this point.
So we do the stuff in the parentheses. So that's negative x squared, negative 6x. It's just 3 squared. Oh, I get it, Mr. Jones. I got it.
I still don't.
Okay. Yeah, that's your problem. That's why you ask questions. You should already know. All right, so now we're just going to multiply. So when you're multiplying, we call it distribution. So distribute x times x is x squared. X times negative 3 is negative 3x. X times I is xi. Yes? I'm going to now do the next number. Negative 3 times x is negative 3x. Negative 3 times negative 3 is positive 9. Negative 3 times I is negative 3i. Okay, then I have another one to go. Negative I times x is negative xi. Negative 3 times negative I times negative 3 is a negative times a negative makes a positive. And negative I times positive I makes, which is what? Negative 1. Remember, I squared equals negative 1. I squared equals negative 1. Now at this point, all you're going to do is go through and eliminate and or combine like terms. I didn't have enough room to go vertically, horizontally, in case you're wondering.
Yeah.
All right, so I have x squared and x squared. What does that make?
What is it?
2x squared? Huh? We're combining like terms. So we had, oh, sorry. No, don't do that. Don't do that. My bad. Ignore that. We're not there.
Yeah, I was trying to think. Man.
Yeah, that's still multiply. Combining here, does x squared have a friend? No. Now we have negative 3x, any more x's. So that makes negative 6x. What happens to my xi and my negative xi? They cancel each other out. I have 9 and I have 1. Plus 10. And what happens to the negative 3i's? They cancel each other out. So these are, now you're down to, oh my gosh, Penn, I'm about to throw you. Oh my God. I wish I could. So now we're down to this. You get the 10 from here, you have positive 9 and you have positive 1 because a negative times a negative makes a positive.
Now it's the same thing.
You can do this, but if it's just asking you to analyze, as long as you have no more imaginaries, you're free to graph. And do we have any more imaginaries? No. So are we free to graph? Yes. Once your imaginaries are gone, you are free to graph. So you just put it in the calculator like that.
This whole thing is just to do it, you know.
The whole thing is to get the imaginaries so that I can graph it properly.
Bro. Why is it invented?
Why do y'all keep asking me the why? And I've already answered to the best of my ability.
We're just
We
trying to
just
follow.
don't know.
There is no why. They just did.
I think as soon as it's something you don't want to do, you find a way to escape it.
They created it, now they're making us do it.
You barely do anything.
I'm doing it, man. They don't even do it. They finally created it and they just never did it again. Now I have to learn it in the 11th grade.
Wait, are we doing pre-cal right now? Or is this still algebra 2?
We're in Creeko.
Okay. And you said algebra 2.
The review part is knowing what a factor is, knowing how to factor, understanding what a zero is, knowing how to distribute, aka FOIL. So those are things you should already know.
Yeah, but we're reviewing it right now.
No, we're doing.
We're applying what you should already know.
Yeah, but we're reviewing it
No.
by practicing it, so.
No.
We're applying prior knowledge. Yes.
You wanna say
Yes, FOIL is just a shorthand way of saying multiple distribution. But that's what it is. It's gonna be a long year.
Oh, my God, we did already.
I mean, I need to start it. I don't know about that.
So how come that's
Huh?
How come that's Facebook and normal browser? Wait, why?
Because I gotta zoom out.
Oh, I wish I was-
All right, so when I look at this, I do not see my full graph. Does that make sense?
Yeah.
So I'm gonna go ahead and zoom out. I'm gonna assume that I need to zoom out a little bit.
Why isn't it popping up?
Your graph, oh, there it is.
Anytime you want your graph to stop thinking, just press Y. My X-min, let's put it at -10. My X-max, let's go up to 100. See what you do. On my Y scale, count by tens. And we're gonna do the same thing on Y, just to see what the view is. We'll do -10.
How does it click way out?
Oh, fudge. Okay. Mhm. Yeah.
Like, I zoomed way out. How do you know that it's not? Yeah, how do we know it's not just regular looking ground?
Because of the imaginaries, there should be a floating max and min somewhere. Otherwise,
Where like, we're like, you, distribute them or fact.
that did not work. Stop doing that. Oh my gosh. Please don't tell me I made a mistake.